Okay. Anytime you add something, you're actually going to increase the rate, and we need to represent that on a graph. So in this sample problem, it says explain in terms of the forward and reverse reaction rates what will happen when we add some iron 3 chloride. So iron 3 chloride is soluble in water. It separates into iron 3 and chloride ions. The iron 3 ion is the only one that's relevant to us because it's the only one that's in the equation, okay? So here we are adding some iron 3. Iron 3 is a reactant. You always shift away when you add things, so that's why we are going to shift to the right, okay? Anytime you add something, look at where it is. If it's on the reactant side, you're going to increase the forward rate. If you add it to the product side, you're going to increase the reverse rate, okay? So let me show you what this looks like on a graph. So if you come down here, at the very beginning, at the initial equilibrium, here you can see that the forward rate and the reverse rate are the same because the length of the arrows are the same. On the graph, that's what these two lines are representing. The solid line is the forward rate. The dashed line is the reverse rate, okay? Now, remember how I said that anytime you increase the concentration of something, look at where it is, and that's how you determine which rate will increase. Since we increased reactant, we are increasing the forward rate, okay? Okay, notice the reverse rate stayed the same. Now, for us to get back to equilibrium, the reverse rate needs to climb to meet us where we were at with the forward rate. You'll notice that the forward rate slightly comes down and then the reverse rate increases. So we get back to equilibrium here. This is our final equilibrium. Anytime you add reactant or product, the final equilibrium rates will have both increased, okay? All right, so here is what happened. This spike, oh, it may not let me, there we go. This spike right here is your forward rate increasing suddenly when you added reactant, okay? And then it leveled off and it met the reverse rate as the reverse rate climbed as well, okay? Yeah.
And the diagram on the right, why is it that the rates, even at equilibrium, are still a little bit different?
They're just trying to show you, they wanted to make sure that you could see the reverse rate dashed line. So they should have had them exactly in the same place. That's just how this code did it. Okay. All right, let's take a look at the sample problem on the next page. Okay, in this example, we're going to remove something. So here we're going to remove some SO2. SO2 is a reactant. Initially, your forward rate and your reverse rate are the same. Anytime you remove something, look at where it is, if it's a reactant or a product. If you are removing reactant, that means the forward rate will drop. Okay, so you can see how the forward rate just took a dive. Reverse rate stayed the same. When we got to our final equilibrium, you can see that both rates decreased. Okay? Yeah.
When one rate drops, does that mean the other rate increases? Like when the forward rate drops, then you're removing from the reactant.
Usually when one rate drops, the other one stays the same.
Oh, okay.
and then at the end, they both came down to meet each other. Okay. Let's take a look at some practice problems. Number 1, consider in terms of forward and reverse reaction rates how the equilibrium will respond to adding some NO. NO is a product. Which rate will increase?
Reverse.
Yes. Okay. And then if I go ahead and I remove some Cl2. Cl2 is a product. So which rate will decrease initially?
Reverse rate.
Yeah. And then removing some NOCl. So NOCl is your reactant. What happens to the forward rate?
Decrease.
Yeah, initially just takes a dive. Does this make sense? Okay. All right, now they want us to show how the forward and the reverse reaction rates will respond to a sudden addition of NO at T1. Okay, so here's T1. NO is product. So that means what happens to the reverse rate?
Increase.
It increases. So I would show the reverse rate spiking. Okay. Doesn't matter how high, you decide. Okay. You know that eventually, well, we can draw the stress. This right here is the stress. Okay. So keep the forward rate the same, increase that reverse rate. Okay. This reverse rate will eventually come down a little bit, not to where it was, but it will level off at T2. And then your forward rate will come up to meet it. Sorry, that's not the best graph, but at T2, which is here, they should be relatively level like that. Okay. All right. And then over here, isn't this reverse rate going to come down a little bit to meet the forward rate? So overall, the forward and the reverse rates are higher than they were originally at the final equilibrium. Okay. Last page. Okay. If you're at equilibrium, there is no point in trying to increase the surface area of a solid or add a catalyst. That's going to increase the forward and the reverse rates by the same amount, and you will observe nothing. Okay, but initially, if the initial reactants have a greater surface area, you will reach equilibrium sooner. So do add a powdered solid. Okay, same thing with a catalyst. If a catalyst is added to the initial reactants, you will hit equilibrium sooner. Okay, now, if they say to you, what is the equilibrium position in terms of the percent yield? At this point, you know that percent yield is calculated, right? It's actual over theoretical times 100. We did this back in what? Chapter 4? Okay. So the equilibrium position has to do with whether you're further to the right or to the left. So that means, am I showing like more product or more reactant at equilibrium? So let's say you have this reaction which has a yellow color when the reactants are present and a blue color when the products are present. Okay. So if the solution was green, doesn't that mean that you would have equal concentrations of HP and P -1? So that means we would have a 50% yield. Does that make sense? At equilibrium. That would be our equilibrium position. And then if they say to you the products are favored, be careful about making blanket statements about how much of reactant or product you think is present, okay? You really can't deduce whether the concentration of one substance or another is necessarily greater unless you really know the colors of things. But I would know that you're going to favor reactants when you're less than 50%. And if you're greater than 50%, you're favoring the products. Okay? And I think that might be it. Let's take a look at a couple of questions and a quick check, and then we're done. We're going to skip number 1. We're going to skip 2. We're going to skip 3. We're going to skip 4. Let's go to 5. Here it says a chemist dissolves sodium bisulfite in a solution of nitrous acid. Sodium ions are soluble. So this compound is soluble, which means the HSO3 -1 concentration is, we're not even at equilibrium yet, so I'm not going to highlight that. The following equilibrium is established with reactants being favored. Okay, so that means we're less than 50%. Okay? True or false? Can you infer from this information that the nitrous acid concentration is greater than the sulfurous acid concentration? Here they are. Can you deduce that? In reality, you cannot compare the concentrations of individual things. We don't know if each one of these has individual colors. They didn't tell us. That would lead us to maybe make some sort of deduction, but here you cannot. Okay, I cannot compare the individual concentrations of things. All I can say is whether we are greater or less than 50%. Does that make sense? Okay. All right. So this is false. Okay. And I believe this homework assignment is open. Okay.